When we talk about effective nuclear charge, it is the charge which is felt by an electron once we have taken into account the various factors. Clear? Now, we have talked about the three factors which are going to affect the charge which is felt by an electron. The first factor that we talked about was first distance from the nucleus. Now when we talk about the distance from the nucleus, it's extremely easy to find it out. It's extremely easy. There's no problem with that. Because the distance from the nucleus will be simply given by that formula, that force is equal to K Q1 Q2 by R squared. So R happens to be the radius, Q1 Q2 happens to be the charge of the electron and the nucleus, and F is the force which is felt by it. So that's not a problem. Then we talked about a second factor, charge of the nucleus. Obviously that is already covered up, and that's what we call as ZE. ZE is the charge of the nucleus. So that also is very obvious. But when we talk about the third factor, that is the charge nullified by the electrons present in the same shell and the shell's inner to the given electron. Now this is what we call as the shielding or screening. Now the shielding and the screening effect happens to be something which we haven't talked about as yet. And this is something which is very difficult to apprehend or understand. Well, if I say that there happens to be, we talked about an example of the bonfire, and I said that somebody is sitting in front of you between the bonfire and you, that person is shielding you from the fire, shielding you from the heat. Now this shielding is extremely difficult to measure. How are you going to measure it? How much part is going to be shielded from by you? So this part happens to be a bit difficult to measure or understand. So there was a scientist whose name was Slater. Now Slater gave approximate rules. Be very clear, these are approximate rules which give you an idea about the shielding or screening. अप्रोक्सीमेट रूल्स का मतलब ये है कि चल यार ऐसा मान लेते हैं कि चल इतना ये कर रहा है, इसको अगर 1 मान लेंगे तो दूसरा इतना कर रहा है. It's like a comparison. So when we talk about the Slater's rule, they don't give us the exact values, they give an approximate idea. So as we can compare the various elements, we can compare the various factors. So Slater's rule do not give us an exact value, they give us an idea about it. So that is what we talk about the Slater's rules. Clear? So these are approximate rules which allow us to calculate a bit of screening or shielding effect. Is it okay? That's what we have, approximate rules, shielding or screening effect. The neutralizing or nullifying of the nuclear charge by the electrons present in the same shell or the shell's inner to the given electron is known as screening or shielding. Full stop. It reduces the nuclear charge experienced by the given electron. It is generally measured as a shielding or screening constant represented by sigma or S. This is what we call as the shielding or screening constant. Now, Slater gave us the rules to calculate this shielding or screening constant. Now let us say we talk about the rules which were given by Slater, and using those rules we are going to talk about the shielding or screening constant that can be measured. Okay? So we are going to talk about the Slater's rules. Clear? Let's write the Slater's rules. Be very clear, the rules which I am going to give you are not actual Slater's rule, they happen to be a modified version of the Slater's rule. I am going to give you the modified version of the Slater's rule, and this modified version is more than enough for us. So we are not going to go beyond it. It will be quite applicable for us. Is it okay? So let's talk about the Slater's rules for calculation of the shielding or screening constant. Now what we do is, we'll consider a nucleus here and we consider the shells here. Okay? When we consider these shells, this, let us say we have the electron here. If this happens to be the electron, then we say that this is the nth shell. Nth shell, the shell which we are talking about is called the nth shell. The shell in which the electron that we are discussing happens to be present is called the nth shell. Obviously, this will become n plus 1. This will become n minus 1. And this is going to become n minus 2. And if further we want something like, we can have n minus 3 and so on. So these are going to be the various shells. Now, this shell, be very clear, remember these names, they are important names. This one is called penultimate shell. N minus 1 is called the penultimate shell. Remember this. This is an important word. They are going to ask you same thing. But what is the case in the penultimate shell? This is called anti-penultimate. The n minus 2 shell is called anti-penultimate. Let's write the first Slater's rule. The electrons present in the shells farther than the given shell contribute nothing to the shielding or screening constant. The contribution given by this shell, any number of electrons which might be present in this shell, the contribution to the shielding or the screening constant is 0. The electrons present in the same shell as the given electron contribute 0.35 each to the shielding or screening constant. Clear? So that means, apart from this particular electron, whatever are the electrons present in this particular shell, each of them is going to contribute 0.35. Let us say we are talking about this particular electron. This electron is going to contribute 0.35. This is going to contribute 0.35. This is going to contribute 0.35. Contribution to the shielding or the screening constant, or you may say this much charge they are going to nullify. Be very clear, the shielding or the screening constant happens to be a dimensionless quantity. It does not have any dimensions. So these are pure numbers. These numbers are not to measure something, they are just to compare something. So shielding order screening constant in itself has no meaning until unless it has been compared with some other value. Is that okay? So that's what we call as shielding order screening. So the electrons present in the same shell as the given electron contribute 0.35 each to the shielding order screening constant. Third point. The electrons present in the n-1 shell shell, obviously that is the penalty made shell, contribute 0.85 each to the screening or shielding constant. 0.85.
So why is it different values like 0.35, 0.85?
Why is it not a whole number? Why it happens to be a fraction?
Why is it different number? The 0.5 कैसे आया?
Because this happens to be done from an observation and from calculations. Now be very clear, these are approximate rules which were given by Slater so as to have an idea about how much charge is being nullified by these electrons. Now 0.35 happened to be the number. It wasn't that Slater wanted to have some multiples of 5 or so, but it just turned out to be. Okay? That's how you got it. So it is more of an experimental value rather than a calculative value. Now let's talk about the fourth point. The electrons present in n-2, that is anti-penalty mate, n-2, that is anti-penalty mate, and inner shells contribute 1 each to the shielding or screening constant. यानी this particular electron यहाँ पर जितने भी हैं इनका 0.85 each है. इसके नीचे जितने भी हैं इन सब का 1 है. So all the electrons present in the n-1 shell contribute 0.85 each. The present in n-2 and lower contribute 1 each to the shielding or the screening constant. Now, we are just going to calculate a few shielding or the screening constant for certain elements. Let us take an example. Let's take the example of sodium. Let's take the example of sodium. Now be very clear, whenever you have to write the shielding or the screening constant, you have to write the electronic configuration. And be very clear, when we write the electronic configuration, we are not going to write the electronic configuration. We will write the electronic configuration as far as the energy is concerned, but we are going to rearrange it so that we have all the electrons of the same shell together. That is how we are going to make it. Now, when we write the configuration of Na, it is going to be 1s2, 2s2, 2p6, 3s1. Now let us say we want to calculate the shielding or the screening effect on the last electron, the outermost electron. So, if I want this as the last electron, this becomes n. ठीक है? This becomes n minus 1 and this becomes n minus 2. Not necessarily. Whatever the question says, but in general, whatever questions I have seen, they are talking about the last shell only. Be very clear, there is nothing wrong in asking, let us say n minus 1 shell के अंदर ही आपसे पूछने, let's say they say, what is the spinning or the shielding effect on the electron in present in the p orbital? They can ask you this question. Then this would become the nth shell. But what's the problem with it? You know how to deal with it. Just put the values and get the answer. Now here, we have to calculate the shielding or the screening effect on this particular electron. Apart from this electron, there isn't any electron present in the outermost shell. So, we have 0 into 0.35. This is for the nth shell. ठीक है? nth shell में एक के अलावा कोई और इलेक्ट्रॉन नहीं है. और इसी इलेक्ट्रॉन पे जब मैं वैल्यू कैलकुलेट करूंगा तो कोई व्यक्ति अपने आप को तो रिपेल नहीं करेगा ना. So this electron is not going to repel itself. So this is going to have no effect on itself. So other than this, there are no electrons. So we are going to have just 0 into 0.35. Next, here we have 2 plus 6, 8 electrons. So n minus 1, it has 8 electrons into 0.85. Okay? And then I have n minus 2. This is going to be 2 electrons into 1. So this is the nth, this is the n minus 1, this is the n minus 2. We simply add these 3.
74.
सर 0 क्या हो गया सर?
इधर देखिए, इसके अंदर इस इलेक्ट्रॉन को छोड़कर जितने और इलेक्ट्रॉन हो उनके लिए 0.35 ऐड करना है. In this case, we have only one electron. We have only one electron. यहाँ पे हमारे पास कितने इलेक्ट्रॉन आउटरमोस्ट शेल में? कितने इलेक्ट्रॉन है आउटरमोस्ट शेल में? एक. ये पूछा है.
हाँ.
अगर इसमें एक ही इलेक्ट्रॉन है तो इसको छोड़कर कितने इलेक्ट्रॉन है आउटरमोस्ट शेल में?
0.
कितने हैं? इसको अगर हटा दो तो कितने इलेक्ट्रॉन है? 0. अगर ये 0 है तो 0.35 कितनी बार आएगा?
0.
कितनी बार आएगा? 0. ये है 0. तो 0.35 का कंट्रीब्यूशन इज हाउ मेनी टाइम्स?
0.
0 टाइम्स. अब समझ में आ गया 0 क्यों आया? पक्का? ओके. n माइनस 1 में कितने इलेक्ट्रॉन है? 8. 1 का कंट्रीब्यूशन कितना है?
0.
n माइनस 1 में 1 का कितना है?
0.8.
0.85. तो 8 का कितना होगा?
8 into 0.85.
8 into 0.85. कंफर्म? 8 कैसे आया? बेटा जब तक मैं -1 2s1 2s2 नहीं लिखूंगा तब तक मुझे कैसे पता चलेगा कौन से शेल में कितने इलेक्ट्रॉन? चल, पोटेशियम एटॉमिक नंबर 19. अब ये बता, इसके सेकंड शेल में कितने इलेक्ट्रॉन, थर्ड शेल में कितने, फोर्थ शेल में कितने इलेक्ट्रॉन है? इसलिए लिखा है. और जब तक मुझे फर्स्ट सेकंड थर्ड शेल का इलेक्ट्रॉन नहीं पता चलेगा तब तक मुझे कैसे पता चलेगा n-1 n-2 में कितने इलेक्ट्रॉन है? और जब तक ये पता नहीं चलेगा तो शील्डिंग कांस्टेंट कैसे निकालना? हाँ, ये n का वो तो मैंने आर्बिट्रेरी बनाया है. यहाँ पे तो मैंने इलेक्ट्रॉन डाला ही नहीं है कुछ. Is it okay? Clear? So that is why even before you start doing the effective nuclear charge or the shielding effect, you have to write the electronic configuration. निशान भाई, ठीक है? that clear? What's the value here?
8.8.
Calculate here.
8.8.
This value comes out to be 8.8. Could you please calculate it for a few elements like सोडियम हमने कर ही लिया, आप पोटेशियम का भी निकाल दीजिए, मैग्नीशियम, कैल्शियम, एल्यूमिनियम, गैलियम. Could you please calculate out the shielding and the screening constant for these elements? Atomic number for sodium is 11, magnesium is 12, aluminium is 13, potassium is 19, calcium is 20, gallium is 31. Let us write the configuration of indium. This is the configuration of indium. It will turn out to be 1:2,
2:2, 2p6, 3:2, 3p6, 310, 4:2, 4p6, 4p10, 5p1.
what I have done is, I have grouped the orbitals having the same n value together. So,
0.7.
this is n.
0.7.
This is n minus 1,
18.
n minus 2, n minus 3,
And
n minus 4. Okay? This is NH shell. And in the NH shell, except for the one electron that we are counting on, that we are calculating the value on, apart from that, everything else has a contribution of 0.35.
Yes, sir.
So here it's going to be 2 into 0.35. This is 8. Now this is 18 into 0.85. This again is 18 into 1.
8.
This is 8 into 1. This is 2 into 1. And each of these are added. The total value comes out to be. This is 1. So I have put all the orbitals of 1 together, 2 together, 1, 2, 3. I have put them together. 4 together, 5 together. Now 5 is the maximum value. The one which has the maximum value is 10.
Sir,
N minus 1, 2, 3, 4. Now we talk about something called the effective nuclear charge. Once we have calculated the screening constant for each of them, this is what we have calculated is called the screening constant.